fire barriers to save properties. It was like beginning of the study of like potential how elementary speed can be in the future designed as a fire barriers. So here, just joined WPI October 2016, and since then I was working on different projects related to all fire or related to other areas, again in fire. So this is like, we recently started this project. It's not a project actually, it's like a preliminary study to potentially be funded in the future. So as you know that, so interacting fires or merging fires can happen in any situation. So is it like in an urban areas, like in multiple houses in fires, the two sides of the roads maybe just merge, or with oil and tanks, because the multiple oil tanks like fires, they still can merge. But for the wildfires, we have this problem frequently in different fires. If you go back and just look at the post-fire investigations of different fires, you can see that the major concern for the firefighter was merging of the two fire lines. So this actually was very deadly and costly. So some of these examples of the fires are from Black Saturday or Black Friday, like Australia, and also fires in Portugal last year, fires in California last year, and this year even Northern California fires. I just found it in the news, actually. It was not a report, but I just could see the interviews of the chief firefighters that they were actually they were mentioned about the fire emerging, and also San Diego fires were in 2007. That I can list more even, but this is just examples. So what we know so far about the emerging fires, emerging dynamic of fires, is very limited to some like burning fires that we use like the information for, mostly for the house fires, how the house fires merge. So burners are very different from the diffusion flames because you don't have that heat feedback from the flame and how it affects the fire spread and the heat release and also flame height. So that was motivation to start this work, because we don't have that knowledge of how the fire dynamic of emerging fires. So for that, we started planning some preliminary like laboratory scale experiments. So we used two pans for that replicate the shape of the fire lines with 0.2 meter by 0.8 meter, different spacing like a parallel configuration and also angle configuration, which is very common in forests, because you have the fire lines, they can merge at any angles, any random orientation. So we have just some preliminary capturing by videos, HDD cameras and also thermal cameras, and also measuring the mass loss with the load cell, and also some temperature at different locations in the center of two fires. So, so based on what we got from the experiments, the two configurations are not similar. So you see the mass loss rates of two different configurations here, plus the reference fire of a single fire that we burn in the lab for getting the data from that fire. So you can see the mass loss for the reference fire is much lower than when you have two fires interacting. So it starts from the 10 centimeter to 20 and then 30. But what is very obvious here is that with the angle configuration, you have higher mass losses. So you have higher mass losses, that means higher burning rates, more heat release rates, and more fire spread. And also, if you look at the temperatures, you have more steady temperature between two fires when you have angle configurations. So starting, this is like a central area of the two fires. So you see that like a peak shape of temperature with the pilot configuration, and also you've got very steady with oriented like a angle configuration. So then based on that, we did some analysis that found that with the angle configuration, we have limited of air entrainment. So that's makes it more easier to understand that why we get these results. But as this project is undergoing, we still do like a data processing, so I don't have that all data. But this is like a burning rates. You can see that the burning rates here for the reference part, this is like separated by 2 bands. Here you have reference part here. You see all interacted parts have the higher burning rates, and especially the angle configuration is much higher even than the pilot configuration. Yes?
What are the units?
Oh, sorry, that's a gram per meter square per second. Sorry. So currently we design another project to see the scales, the problem of the difference of the results with the scales. So we have 2 different scales, and I think I have 2 minutes. I want to show this some more understandable. So you can see here a 1 meter pan with the pilot configuration with the 10 centimeter distance. Over there is an angle with the 10 degree configuration, and a reference part which is one single part which is burning by itself. So, and you see the scale on the left. So now you see the starting of the merging. I just want to show you what happens. And so we see that the flame height is changing continuously with 2 interacting fires. So starting to be higher and higher, just so it goes over about 2 meters. Then what you can see is just losing, like a flame becomes shapeless. So you've got flame goes in on and off, goes to the side and between the fires, and also here on the right side. So if you imagine that this fire lines, like the board is just like 10 meter, 20 meter, 30 meter, how much is the scale of this merging problem? And now we come almost, the tip goes to the 3 meters. And you can see here the behavior of the angled configuration is more erratic just than the pilot configuration. So you've got the flame gases goes underneath the pan, and then
I think we have to cut short the presentation because we're too close.
yeah, I think that's. I'm sure the last minute, so yeah, that's. So just what we're doing now is just doing the data process of mass flow, temperature, pressure, flame velocity, and height, and also some simulation with the FDS, and potentially writing a proposal for more effects of wind, topography, orientation, and also doing some larger scale to compare these laboratories with larger scale to see if we're missing any behavior. Thank you so much.
Thank you.